Good afternoon.
Good afternoon. Good after morning. So, any questions, lingering questions on Lab 1? Yes?
Should we include code in our
Oh, yes. So, formatting Lab 1. The example lab reports that are on the policy page have two different formatting options than you are going to use. Number one, you are not going to put your homework into your lab report. That's a lingering artifact of the days when we had homework due with a lab report. You've already handed in your homework. Do not put your homework in your lab report. Number two, in the bad old days when those examples were generated, we had people hand in their homework on dead trees. And so we wanted to minimize the bulk of paper, and therefore we had them not put code in. In fact, in the examples, we truncated the code because we didn't want to give everything away. But you are going to put your source file in your lab report. It's all electronic, no trees need suffer. You're going to put your source file into the lab report, but not the libraries, not config.h. If you change a frequency, do a one-liner in the lab report saying we changed the clock frequency to 640 megahertz in config.h. One line is all it takes. Don't include config.h. Don't include protothreads.h. Just your source file or files with your thread descriptions and main. Okay? So that's what we want for Lab 1. When in doubt about what your TA is looking for Lab 1 report, ask them. But they're going to want to see source code. Any other questions on Lab 1? I already had a question on Lab 2 for today, and let me show you how I think I would implement it. It's not unique, but you're going to have the PIC 32 SPI channel. I'm going to talk a lot more about SPI channel, but there's a clock, a data line out, MOSI, a data line in, MISO, and a chip select. And you're going to run those four over to a DAC, a microchip DAC, which is a dual channel DAC. It has channels A and channel B. Each of the two is a 12-bit channel. You can load both of them in less than 5 microseconds if you want. You don't have to load them that fast. The system will support a clock rate of, I believe the spec sheet says 20 megahertz. The whiteboards behave a little better if you run the SPI channel at 15 megahertz because the bandwidth limit of the whiteboard is right around 20 megahertz. Above that, it's a short circuit. So if you leave it to 15, you get a little bit better looking clock response. Over this port, you can sequentially send channel A and channel B. It's a serial line. Each channel update is 16 bits. Running at 15 megahertz sounds like 1 per microsecond. I would suggest using one channel for the DTMF and the other channel for the voice. We have stereo speakers they're going to map in an obvious fashion to these outputs. You plug the stereo speaker into it, you'll get voice in one channel, DTMF in the other. You can debug by moving them to and from your ears. There's other ways to do it. My assumption, which I'm going to go through in some detail today, is that you're going to be running a direct digital synthesis sine wave generator, actually two of them, one for each of the two DTMF frequencies, plus the voice channel, all at the same rate, so that you can output all the samples synchronously from one interrupt service routine. You could, if you wanted, write 3 different interrupt service routines, all running at a different frequency, add together the samples somehow, and output them. But I think you're going to want, for simplicity, for sanity's sake, minimize the interrupt service routine complexity, write one interrupt service routine, which is running at a fixed rate, which you get to choose, and put all of the synthesis in that subroutine, interrupt service routine. Any more detail? So last time I talked about keypad, I sort of did a teaser on direct digital synthesis, probably just enough to be annoyingly confusing. But what we're going to do is we're going to take some variable register. I tend to say register because I originally implemented this in Verilog, but we're going to take a variable. It could be an int, a char, or a short, and I will tell you what the difference with what difference that makes in a minute. And then we're going to increment this thing. We're going to feed it back to itself. So we're going to increment this variable by a fixed amount, which is going to be proportional to the frequency out that we want of the sine wave. So we're going to come up with a scheme that allows us to linearly map an increment of a variable into a sine wave of variable frequency. And once again, the central abstraction is that every time this variable overflows, it is the equivalent of wrapping a phasor 0 through 360 and back to 0. So that the larger we make the increment, effectively what we're doing is we're speeding up the phasor as it rotates, corresponding to a higher frequency. I said last time what I did was to implement this with a 32-bit register, but you can't have a 2 to the 32 entry table because that's gigabytes. So what we're going to do then is use the top 8 bits as an index into a sine table. We're going to index through the sine table. We're going to take the top 8 bits. We're going to map it into a sine table. And then the value that comes out of the sine table is what will be transmitted to the DAC. This has a couple of implications. One is that if I'm asking for a very low frequency, that I might put out, since I'm incrementing down here at the low end of this variable, there's 24 bits here before we change something that's related to the table, at very small increments, I might put out the same sample. I might put out the same value for several sample times in a row, and then step up to the next sample and then to the next sample. That's okay, because it's still going to be the case that for one whole cycle you have 256 different values, and you can show that the main error term, the first major error term, is up at about the sample frequency. Fourier error term is at the sample frequency. At very high frequencies, where the increment is going to be up here someplace, at very high frequencies, you might have a sine wave that looks like this. Clearly there, the distortion is going to be so high that you'll be able to hear the difference between the waveform and a pure sine wave. And so one of the homework questions asks, how many samples does there have to be on one cycle of a sine wave before it's sine wave enough? Before it's sufficiently sinusoidal. So the whole DDS generator is going to be 2 lines of code. We're going to increment a variable. We're going to do a table lookup. Then there'll be another line or 2 lines which actually transmit that value to the DAC, because we have to do some sort of manipulation to get the SPI to run. That's it. Oh, we have to build the table, but that's done once in main, where you can afford to do a lot of floating point arithmetic. The main question we still have to answer is, what's the relationship between the increment and the actual frequency? I said it's proportional, but you need to know the proportionality constant. So one overflow of the register is 1 cycle. Right? One overflow of 32 bits is 1 cycle. That means that the system is going to take 2 to the 32 sample times to overflow if the increment is 1. So then the frequency of the output, F out, this is the sine wave out. Sine wave out frequency is going to be given by the sample frequency divided by 2 to the 32. You have to tick the thing 2 to the 32 times. This is the rate at which you're ticking it, is at Fs. So this is the sample frequency. That would be the frequency at which you're running the interrupt service routine. So for an increment of 1, this is the frequency of the sine wave that comes out. Oh well, let's say that we're sampling at some nice number to calculate with, like 2 to the 13th. That's 8,100 and odd samples per second. So if we have 2 to the 13th over 2 to the 32, it looks like we're going to be having a sine wave running at 2 to the minus 19 hertz. How many weeks is that, folks? How many seconds are there in a year? Well, it turns out there's about pi times 10 to the 7th seconds in a year. It's a good number to remember. There are, really. And that's approximate. And so this is a truly small number. This has a period of years. You know how to convert base 2 exponents to base 10 exponents, right? You divide this by 3.2 and you get the base 10 exponent. So this is like 10 to the, actually, so 2 to the minus 19 then is something like 10 to the minus 6. Oh, that's only a month. This is a cycle per month. Now, let's say that we make the increment 2 rather than 1. What's the frequency? It's twice that. It's still very small. If we make it 3, it's 3 times that. That says that we can control the output frequency to any value down to 2 to the minus 19 hertz. Well, that's absurdly accurate, but it's accurate enough for this lab. What is the accuracy requirement for this lab? What? 1.5%, right. So you say, oh, that's ridiculous. What's that fool thinking of? Let's use a short. So now, if we use the short, so this is for this would be for a int. So for a short, we would have that the frequency is fs over 2 to the 16th times the increment. So the basic increment at 8 kilohertz would be 2 to the 13 over 2 to the 16, which is 2 times 10 to the minus 3 hertz. So that's about 1/10 of a hertz or so. Is that accurate enough for this lab? I see one positive head shake. Is it better than 1% at 700 hertz? Yes. Okay, so now we say, well, if you're only going to use the top 8 bits for the table, let's just make a 10-bit, an 8-bit register, which would be a car register, a car variable. So now we ask what happens if we set the register length to 8. Now we have fs over 2 to the 8th, which is 2 to the 13th over 2 to the 8th, which looks like 2 to the 5th, which is 32 hertz. And that's not good enough. That's about 5% of 700 hertz. So you need the extra bits in the register, in the variable. You need the extra bits in the variable to give you sufficient accuracy in the synthesis. They're not used directly as an index. They're used as fractional index values. They're used as tiny fractions of the index that allow you to step much more slowly and carefully through the table. Okay, so any questions on that? Yeah.
Could you please explain why that's good enough?
That's 1/8 of a hertz, right? What's the lowest frequency you have to synthesize? What's 1/8 hertz over 700 hertz? 0.001 or something, right?
Is it the same if you like use float?
You cannot use floats. They're not fast enough. You have to use fixed point. I think you'll find that you won't be able to go. I believe that a floating add takes 80 or 90 cycles, and a floating multiply is 30 or 40 cycles. So I think you're not going to be able to go fast enough. But I'm not sure. Have you tried it?
Yeah.
Does it work? At what frequency synthesis?
Like basically all the DTMF.
What frequency of interrupt service routine?
Made that. It's the clock is 40 megahertz and the service frequency like 5,000.
What's the frequency? 8 kilohertz. Right? So maybe on this architecture, a floating point will work. I would never use floating point in interrupt service routine because it cuts into the performance quite significantly. This requires an add and a shift, which is much faster than doing a floating point multiply. In this case, you could probably get away with it by lab 3. If you use floats to do the work on this processor, you won't be able to do the lab. So you may as well get used to fixed point. You can think of this as a fixed point number with the binary point right here, where this represents one index value. Okay, any other questions, comments? Yes?
Where did you choose to, or where did you get to the 13th chromosome?
I said, let's assume that we're going to sample at 8192 hertz, which is about the lowest you can sample. All right, so now we know that the frequency of the sine wave out is given by the sample frequency of your interrupt service routine divided by the register length, in this case 2 to the 32, the register overflow time, times the increment. Double increment, you double the rate of the phasor, rotation, you double the frequency. Well, that means it's easy to choose the increment then. The increment that you choose is just going to be the frequency out times 2 to the 32 over fs. So if I ask you to do 797 hertz, you know what increment to set. So you're going to build a table of increments. And play 2 of them. So in fact, you're going to have 2 phase accumulators. You're going to have phase 1 for the first DTMF frequency and phase 2 for the second DTMF frequency. And they're both going to point into the same table. And then presumably you're going to add those together to make the sine sum for the 2. Now there's a few details to make sure that the scaling is all correct. The first detail is that it's handy to add sine waves that happen to be centered around 0 because you know that the average value is 0. So you're going to want to say have a table whose values go from 0, it's a 12-bit DAC, so we want this to go from minus 2 to the 11th to plus 2 to the 11th, which is 2048. So we want this to go from minus 2048 to plus 2047, because 0 counts as a positive number here. And we want this to go, of course, to 2 pi, but 2 pi is not a good index. So we want the indices to run from 0 to 255. So we have to do some scaling to get the sine into the correct scale. And when you add those together, you're going to add two signs together at two different frequencies. So really you can't go all the way to 2047 down to minus 2048, because if you add them together, it's going to overflow. Why is it going to overflow? Well, the DAC is not 2's complement, it is offset binary. So it assumes, on the DAC scale, it assumes that this value is 0 and goes up to 4095. So the DAC is offset binary, so that every number that is fed to it must be between 0 and 4097. We can't handle negative numbers, which means that what we're going to have to do in the interrupt service routine is add sine 1 plus sine 2 plus 2048. And if that number ever overflows, you get a very characteristic waveform that's easy to recognize. And it's going to look something like this. You expect to see something that looks like this, and what you're going to see is, it's so messed up I can barely draw it, is you're going to see something that looks like this. You're going to see chunks that are disconnected with a very fast transition between them. And when you play that, it sounds nasty. Why does it sound nasty? Because every sharp transition is a broad spectral, generates a broad spectral component in Fourier space, which comes across as a or a crackle or a hiss or growl. It'll sound broadband. That's all I can say. You get so you can recognize the sound of overflow distortion. Sad but true. So you have to scale these tables so that the sum never overflows. So let's look at a little bit of code here. Oh my, it hasn't been, oh there it is. All right, so I've been playing around with, this code is what I've been geeking it up with for the last 2 or 3 weeks. And what I wanted to do was to use a DAC to produce a nice clean sine wave, feed this into some complex impedance, and for testing I'm just using a RC circuit with a cutoff of 10,000 radians, and then feed this back into the ADC, measure the voltage, compute the phase and the magnitude. So what I'm going to show you is code that does that, but buried in there is the direct digital synthesis for doing the sine wave generation and the interface to the DAC. You can ignore the ADC stuff for now, although it could be interesting. It's not relevant to this lab. So there's a command sequence that you have to use with the SPI DAC. The high order bit 15 of the 16-bit word that you're going to send to the DAC is whether you want A or channel A or B. Bit 14 is don't care, set it however you like. Bit 13 is a gain selection bit, and you must set it to ×1. And bit 12 is shutdown control bit. You obviously want it active unless you want to turn off the DAC. So the top 4 bits then are the command, and then the bottom 12 bits are the data, 0 through 4096, that you want to send. So there's the command for a DAC config for channel A and for channel B, which we can then OR with the data down lower in the code. I happen to be sampling at 200,000 samples per second. You're not going to go anywhere near that fast. We include all of the plib stuff. And oh, by the way, for this code, the CPU is running at 60 and the peripheral bus is running at 30. So the SPI clock divide of 2 means run the SPI channel at 15 megahertz. I don't expect you to switch the clock speed. I was doing this because I wanted to see how much performance I could get out of the chip. It's a bunch of fixed point arithmetic stuff we'll talk about later. But the meat of the matter is the interrupt service routine. And SPI, the SPI signals go like this. To signal a peripheral chip that you're about to send it a command, you bring the chip select low. Yoink. You're done with the command, you bring the chip select high. Once the chip select is low, now you ask for an SPI write, and you give it some data. At some later time determined by the hardware, the clock starts, clocks out 16 bits, and stops. You have to wait till it is done and then raise the chip select line. If you raise the chip select line before the SPI transfer is done, you will truncate the data. Actually, let's not start with this one right yet. Let's go back a level. Back a level. Go to the SPI page. Oh, thoughtfully wrote the SPI page for you, which has the chip, the pin out for the DAC. This code is not a threaded code, which is why I didn't think of it initially. This is right out of the plib examples. And all this does is to generate a generates a ramp. So I was testing my understanding as well as the linearity of the DAC by saying that the DAC data is equal to the previous DAC data plus 1 masked with FFF, which happens to be 12 bits. So the first thing we're going to do to start the transaction is we're going to set port B to 0. That happens to be what I'm using for chip select. So in my case, this is B.0, but you can choose any pin you want. There's nothing special about that. We clear the bit, start the transaction. If you know that the SPI bus is always going to be ready, you don't have to do the test to see if it's ready. But this will do a test and hang here until the SPI buffer is empty. If the interrupt is slow enough and no other process is using the SPI channel, then you can just leave that out because it'll always be ready. The obsessive programmer will put this in, get the code running, and then take it out and see if it still works. All right. Then we do the write to SPI using DAC config channel A plus the DAC data. The DAC config channel A was just that the high order bits to set the channel A load. Then we hang here until the SPI channel is done, then we set the port bits high. At that point, the transaction is done. When the chip select goes high, the voltage appears at the output of the DAC. So this computes that thing that's off the screen. So this computes the new value of the new voltage to be output. This transfers it to DAC, and when the transaction is complete, the voltage appears on the DAC output. Questions? When you want to go for high speed, if I wanted to eliminate as much of the waiting time as I possibly could, because I wanted to run a system at high speed for doing this impedance testing, I didn't want to wait for the channel to be done if I knew it was going to be done by the next time I got to the interrupt service routine. And so I folded the code to clear the chip select at the beginning of the next interrupt service routine. And as you'll see in the next code, then the code has been folded. So the first thing that happens after we clear the interrupt flag is to end the SPI transaction from the last interrupt. That means then we don't have to wait for the this SPI write to be done. I do a bunch of arithmetic afterwards because I wanted to fold as much into the interrupt service routine after the write as possible, but it does not wait for the interrupt to be done or for the chip select, for the SPI transaction to be done, because I knew that by the time I got back to the interrupt, the transaction would be complete. So we end the transaction. Then I did a bunch of arithmetic here to get the quadrature values. You know what quadrature demodulation is? Quadrature demodulation. I was quadrature demodulating the sine wave coming back, low pass filtering it. These are slightly weirdly formatted RC low pass filters. Then we start the next transaction by clearing the chip select. We're not going to wait for TX buffer ready because I believe that it's ready. Then we write SPI. We write the SPI channel. Increment the phase accumulator. Ah, that's the DDS line right there. Increment the phase accumulator. Look up using the phase accumulator shifted by 24. That's the top 8 bits. Use the phase accumulator shifted by 24 to load DAC data for the next time through the interrupt service routine. That's the entire DDS right there. Now, this is more complicated than you're going to need. In particular, I generated 2 tables, one for the sine and one for the cosine, because I was doing quadrature analysis. I was doing phase and 90-degree out of phase signals. So I needed a sine and cosine table. But you are only going to generate one table and index into it twice with 2 phase accumulators. So we're floating an index. We're generating a table of some sign table size. In this case, it happens to be 256. We're taking the cosine of the float of I times 2 pi divided by the number of samples in the system. We're multiplying by 2047 so that we have a full scale sine wave, full output sine wave, and just storing it as a int. So we're forcing these floats into ints and storing the ints. So that when we look them up in the interrupt service routine, so when we look up this cosine table in the interrupt service routine, we'll get a value proportional to the cosine times 2047 with a phase given by the 8-bit value phase accumulator shifted by 24. So in the midst of all this, it's these two lines are the direct digital synthesis. That's it. It's embarrassingly easy. That's why everybody uses it for generating sine waves. These two lines. Any questions? Let's go back to the canonical PLIB stuff, serial peripheral interface. So this is slightly more straightforward. You'd, instead of having DAC data generated as a ramp here, you'd have two lines here for the direct digital synthesis, and then this is exactly the transaction you need to get the SPI running. I'm going to talk more generally about SPI next time, because there's a couple of quirky things you need to do, but the basis of it is you're sending a serial burst that's generated in hardware. You load data into an SPI register, and the coprocessor, the SPI coprocessor, turns on, generates 16 clocks, clocks out the serial data, turns itself off. Yes?
Also for the DAC, SPI DAC, it's like when I'm sending out information to, like, for example, one of the channels, I can hear like some noise at another channel.
Okay, what kind of noise?
It's just like some periodic like noise. Like.
So put it on the scope and show me, so we can look at the Fourier transform of it and see what it is. It could be clock noise. It could be that you're hearing some subharmonic of the clock because of a periodic output. I don't know without looking at it. In any case, it shouldn't. Is it loud?
It's not loud. It's just like
A little bit like. So I'd like to hear it, see what it is, because I don't know. What else? These DACs are pretty nice. They have, so the DAC itself is very straightforward. It takes a supply voltage, a ground, a chip select, clock, data in, no data out because it doesn't generate data. It has two voltage outputs, and this thing called LDAC. LDAC allows you to synchronize the update of the two outputs. So you can load channel A, hold LDAC high, load channel A, load channel B, drop LDAC, and both A and B channel will appear at the same moment if phase matters to you between the two channels. If you want to simplify the interface, which for this lab is just fine, you just ground that. You just drive that low, and the channels will output as soon as they are ready. Internally, there's a 12-bit voltage reference, stable voltage reference, that gives you at gain 1 exactly plus or minus 1 volt output. It's really nice. It's fast. It's rated at 200 kilohertz, I believe, but I think that, let's see what it's rated at. Fast settling time 4.5 microseconds, which is to say 200 kilohertz settling time. You can, however, run this at least twice as fast if you want to generate high frequencies. However, if you want to go for very high frequency synthesis, let's say you want to generate a radio signal, then you can use an external parallel DAC. I'm not suggesting it for this lab. You can use an external parallel DAC and feed the parallel DAC with DDS samples by direct memory access. And then you can get 3,200,000 samples a second. I would say for this lab, you're going to want to be in the region of 8 or 16 kilosamples a second. Any questions? There is a lot to plow through for Lab 2. I want to talk a little bit about SPI next time in general, although you could also read some on the SPI page. And I want to talk a little bit about speech production next time, how we're storing it, how we're playing it back. But you've got plenty to work on for Lab 2 right now. We've got about 1 minute or so, 3 minutes maybe. Final projects, ideas. Any ideas? No matter how crazed, let's hear them. It would be fun to try and make a precision impedance meter. In 2 weeks, I've been able to get the phase within 5 degrees and the amplitude within 10%. That's horrible. So, what are the error mechanisms and how do you fix it? Sounds like a out in the weeds final project. It could be interesting. How about one thing I've always wanted? I mean, you're digging into a circuit. You've got a voltmeter in your hand. You're down like this, and then you have to hold your hand still and look over at the meter. Why isn't that meter talking to me? Right. So a talking DVM would be very nice to have. Maybe with some amusing error messages when you short something or something. So think about it. Speech has all kinds of uses, but I will see you in lab, well, I'll be in lab this after. Wait a minute. Today is Monday. It is Monday, right? Yes, Monday. See you tomorrow.